in person at the moment for, well, for complicated reasons to do with visas, I gather. Stephanie got her start on studying scientists, or studying the sociology of science, at King's College, not the one down the road, but King's College, New Brunswick?
Halifax.
No, near enough. Near enough. She then moved on to the University of Toronto. She then moved on and did a PhD in Harvard, was a member of the Harvard Society of Fellows, and now she's moved to the US to start a regular academic job in Pittsburgh. So it's a great pleasure to welcome Stephanie. She's going to switch over, so most of the talk you'll see the slides and hear her voice, fingers crossed. And then we'll have a bit of time for questions at the end. So, thank you, Stephanie.
Thanks so much. Okay. How's that?
Good. Yeah. That's good, yeah.
Okay, great. Well, thank you so much to Jeremy and to Ursula for inviting me to be a part of the workshop. I'm incredibly disappointed that I can't be there to join all of you this week. I often say that I'm writing the very preliminary, very early history of what actually happens later when computers get introduced to mathematics, and I suspect that the work that all of you are doing and the questions you're asking are shaping that history as we speak. So I would have been so excited to be there. I have a lot to learn from all of you. So I'm a historian of science by training, and the kind of history of science that I work on, generally speaking, is interested in questions about how knowledge is made, who it's made by, with what tools, according to what standards, and for what reasons, in different times and places and different communities. We're interested in how different institutional and political contexts, how different material cultures and intellectual landscapes enable and constrain different communities to ask and answer quite different questions from one another throughout history. We look for continuities, we look for discontinuities, reasons for change. We even look for evolutions in what and how we know and who knows it. And I'm interested in particular how different communities have introduced modern digital computing to the knowledge that they want to make, to their daily practices, to their ways of thinking, and specifically, of course, how in the very early moments of digital computing in the mid-20th century, people came to think about mathematics and about theorem proving in new and different ways. So proofs, of course, are meant to be general and correct. They're meant to establish the truth of some mathematical proposition for all of the relevant cases in all times and places. But of course, as I probably don't need to convince you, proof also has a history. What counts as a proof, what standard demonstrations are adhered to, change over time and in the hands of different mathematical communities. And different kinds of demonstrations have sufficed to convince certain communities of the truth of some fact, but not others. So a classic example is that there were times and places where diagrams were a common, if not central, component of the construction of proofs. At other times and places, and especially in the 19th century, there was some anxiety and suspicion about diagrams and whether they could serve to establish the fact of a thing in mathematics. Similarly, different assumptions, different rules of inference are put to work in certain places and times and not in others. And I'm interested, or historians of mathematics in my community are interested in unpacking those different standards of demonstration that communities subscribe to in different times and places. And of course, the advent of computing, and with it, the possibility of automation, the character of proof and new possible practices and tools for making and doing the work of proof were on the table. And that is what I'm excited about. So beginning in the 1950s, some communities started working to get computers to produce mathematical proofs. Computers made possible, as you all know, new and very exciting possibilities for the work of proof because they're so powerful and efficient and accurate at rule following. But there have been times when computer-assisted proofs have also been controversial. Many of them are too long to be read all the way through, so although they are fully formalized and known to be correct, they're not surveyable, and this created some anxiety, especially in the 70s and 80s. Some computer proofs, of course, make use of operations that are not easily followed or understood or apprehended as correct by human readers. There was some discussion about whether or not these should count as proofs at all. But that is not my question. I'm not in the business of adjudicating what ought to count or not count as a proof. I ask a sort of prior question. And I wanted to know how proofs on the computer were made and made possible in the first place. I wanted to know what was actually involved on the ground in getting computers to do the work of proof in those early moments in the 50s and 60s. I wanted to know some seemingly trivial things like who paid for it, what institutional contexts were amenable to doing this kind of research and which were not. But I was also interested in the intellectual questions. What new ways of thinking about mathematical objects, what new practices of production, what new ways of thinking about what mathematics is and how it works emerged in these moments when people started working with computers to do this work. And at the most fundamental level, I'm also interested in what happens to mathematical agency, how the work of doing proof was redistributed between people and machines, between different kinds of people with different training, programmers and logicians and theorists, contributed a different kind of work to early automation. So I'm working on a book project that's based on the dissertation that I finished 3 years ago that is a very early history of automated reasoning from about the mid-1950s until the 1990s, and I'll share just a little bit of that work with you today. My goal is to situate the field in the history of computing in the United States more generally, and also in the longer history of how we think about what reasoning is and understand human reasoning faculties. And I'm very interested in the early history of this field, in part because at that time, the limitations and the possibilities of computing were not yet well understood, either practically or formally. It was not so obvious what kind of tool the computer would turn out to be, what it would be good for, what it would not be good for. So there's a lot of really imaginative speculation going on about what kind of tool the computer was at that time that I'm really interested in. But I'm also fascinated by the early field because so many of the practitioners working in it, some of whom we'll talk about today, and some of whom might be in the room with you, disagreed about really interesting elements of the work. There was some disagreement about the character of human mathematical faculties, like intuition, like reasoning, like understanding. There was some disagreement about the degree to which computers might be made to possess or simulate faculties like that. And of course, there was some disagreement about proof. What kind of proofs we want, why we want them to be that way. Here is some examples of some of the early, usually anthropomorphic language that is used in some of the early visions of computing proof to imagine what kind of contribution the computer might be able to make. So there were those who wrote about the computer at one end of the spectrum who imagined that computers might become quite a lot like human mathematicians at some point. They could be like a colleague or a mentor or a coworker. Others were less optimistic, imagining the computer might be more like a graduate student or a high school student, capable of making a contribution, but only with a lot of guidance, and the significance of those contributions might be limited. And still others used the language instead of servitude and slavery to talk about the kind of contribution they thought mathematics would be able, or computers would be able to make to mathematics, namely mostly by the repetitive performance of more menial tasks. And so part of what I'm interested in is recovering these different anthropomorphic visions. What kind of labor do people think is involved in the production of proof? How is that labor divided differently between humans and machines? How are different kinds of contributions valued or devalued in these visions of the computer? But more importantly, I was interested in how these ideas, early ideas or imaginings of the computer got built right into the software that different people designed and implemented. I wanted to know what was involved in implementing a mentor or a graduate student or an assistant or a slave. What did that look like? What kinds of ways of thinking about mathematics and proof were involved in that? And that's what I'm interested in sort of recovering and reconstructing. So today I'll say just a very little bit about 3 of the early programs. I expect many of you are familiar with each of them, but hopefully I'll have something new to tell you about them. First, the logic theory machine that was developed at the RAND Corporation in Santa Monica, California in the mid-1950s. Then the program Q that was developed somewhat across IBM and Bell Research Labs in the late 1950s. and then the Automated Reasoning Assistant, or the AURA, that was developed at the Argonne National Laboratory just outside of Chicago, beginning in the mid-60s and through the 70s as well. And I'll talk about each of these in part because they were early examples of three quite different approaches to the automation of proof, which were drawn upon and modified in various ways throughout the second half of the century. So the logic theory machine was in some ways an exercise in implementing a kind of colleague. It's famously a part of early artificial intelligence, and the goal was to see whether one could program a computer to do the kind of mathematical proving and problem solving that people were imagined to do. The program Q out there was an exercise in implementing a slave. That was the language used by its designer to articulate that while computers in fact might not be like people at all, they can still be very useful precisely because they can follow rules efficiently and untiringly and unerringly. And what can we make, what kinds of proofs are possible with a tool like that? And the AURA was rather an exercise in implementing a kind of assistant that was not meant to prove theorems in a standalone way, but to interact with the human user, and that maybe new forms or new ways of doing proof would be possible through that kind of collaboration. So I'll just say a little bit about each of these programs today and highlight some of the new ways of thinking about mathematical objects and proof practices that I think are some of the interesting transformations that I think took place in the design and implementation of each of them. So starting with the logic theory machine, as I said, it was developed in the mid-1950s, but the story of the logic theory machine, as far as I'm concerned, doesn't begin there. It starts instead in the turn of the 20th century. So the program famously was designed to prove theorems from a canonical early 20th century text in mathematical logic, the Principia Mathematica. It was, of course, written by Alfred North Whitehead and Bertrand Russell, two English mathematicians around the turn of the 20th century. And in it, as I'm sure all of you know much better than I, it's laid out a system of deductive logic, a set of axioms, a set of inference principles. The Whitehead and Russell thought through a kind of logicism was, at least in principle, all you would need to construct proofs of the results of mathematics. That all the theorems could ultimately be proved by deducing consequences from their axioms using their rules. But in addition to presenting this kind of logical formalism, Principia also represents a particular material culture for doing the work of mathematics. It's a book culture, a written culture. Russell, Whitehead, and their contemporaries were in the business of collecting and cataloging mathematical knowledge on the page, in books, in a standardized logical system. But they also went to great lengths to produce a symbol system for writing mathematics, standardizing how it looked on the page. And for them, the symbol system, far from being a secondary or external consideration, was at the heart of their projects. They thought you needed to represent logic a certain way on the page in order to equip the heads and hands of mathematicians to work within the formal system they created. In their introduction, they wrote, "The symbolic form of the work has been forced upon us by necessity. Without its help, we should have been unable to perform the requisite reasoning. It has been developed as the result of actual practice, and is not an excrescence introduced for the mere purpose of exposition. No symbol has been introduced except on the ground of its practical utility for the immediate purposes of our reasoning." And of course, fundamentally, their symbol system was designed to make things easy to see. It was designed to make abstract objects or logical relations or logical inference easy to see, easy to follow on the page. They wanted to make patterns visible, to make structural comparison easy, to make proofs themselves easy to read and follow line by line on the page. And we take this kind of symbol system quite for granted because we all grow up in it. But it's worth noting there is a particular kind of spatiality, a particular kind of materiality, a particular visual character to mathematical demonstrations of this kind. And logical expressions here are meant to accommodate a particular medium, namely paper, the page, the book, and also a particular mathematical agent, namely the seeing, reading, writing human mathematician. And this system, they thought, was designed to give mathematicians direct access and control of their objects of interest, of logical positions, and of work, of inference. And in a sense, one of the questions I wanted to know is what happens to the representation of logical expressions? What happens to the way that inference takes place in the transition from this paper-based book culture to the electromagnetic infrastructure, the magnetic drums of the logic, or the Johnniac machine that ran the logic theory machine in the mid-1950s. I want to quote in a kind of trivial way what that transition looks like. So the program was designed by these two men, Lee and Simon, and both of them at this time were working deeply within the systems engineering context at the RAND Corporation in Santa Monica, California. The RAND, for those who are unfamiliar, was founded in the wake of the Second World War as a kind of research institute, primarily oriented around the question of how the United States could strategize to win future global warfare, especially nuclear warfare. And one of the approaches that RAND researchers took to that question called systems engineering. There were too many variables in imagining what a global war would look like, and so in developing strategies for waging and winning wars, RAND researchers broke the world into different systems. They saw systems everywhere, and they wanted to study the formal behavior of those systems and optimize it. Governments were systems at RAND. The weapons on a plane were systems at RAND. Transportation systems like trains and railways and roads were systems at RAND. They invented the term ecosystem. At RAND, the work was in part about breaking the world into different systems, understanding their behavior, and looking for ways to optimize that behavior in service, in particular, of waging and winning global wars. And so it might seem out of place that a logical theorem-proving program would emerge out of a context like that, but it made perfect sense because both Newell and Simon firmly agreed that both the human mind and the modern digital computer could also be best understood as systems as well, and more than that, that they were the same kind of system, namely an information processing system. Information processing systems were one that took symbolic information as input, manipulated it according to certain rules to solve problems, to formulate judgments, to make decisions, and so on. And they believed that computers could be programmed to process information and therefore to behave like human minds. For them, the material substrata did not matter. It could be the brain, it could be the computer, it could be a system that was a mix of humans and machines or even animals. All that mattered was the high-level formal behavior of the system. And the logic theory machine was their first attempt to actually design and implement a program that processed information in the same way that people do. It was a complex information processing system, an empirical experiment in trying to translate human information processing behavior into an automated system. And the first thing that they needed if they wanted to automate human problem-solving behavior in mathematics was a model of what that problem-solving behavior looked like. And for that, they turned to this man named George Polya, with whom Newell had studied closely as an undergraduate in mathematics at Stanford. And in addition to his mathematical research, Polya was deeply interested in mathematical pedagogy. And he believed, contrary to some idealizations or mythologies of mathematical practice, the mathematicians don't, in fact, simply deduce consequences from axioms in search of interesting and true theorems. They do all kinds of things. Mathematicians start from things that they want to prove and work backwards, looking for analogies or related problems. They experiment with cases, they look for counterexamples, they build models. Mathematicians do all kinds of things. And more than that, and very importantly, Polya did not think that those tricks of the trade were esoteric and inaccessible secrets. He thought they could be identified, they could be formalized as rules, and then they could be taught to students to help make them better research mathematicians. And he wrote in 1954, certainly let us learn proving, let us learn how to deduce consequences from axioms, but also let us learn guessing. And those ways of guessing he called, of course, heuristics. And Newell and Simon took their model of what human problem-solving behavior looks like from Polya. They wanted to design and implement a computer program that looked for proofs by following rules that captured the human heuristics that informed mathematical problem-solving behavior for us. This was a rule-bound model of what human problem-solving looked like. So the logic theory machine, as many of you probably know, had two heuristics built into it in particular. First was that the logic theory machine worked backwards. It did not start from the axioms of logic and worked forward by deduction looking for theorems from Principia. This, of course, would have produced an exponential explosion of data and was ruled out as a possibility earlier in the 50s. The logic theory machine worked backwards, and it worked backwards by a second heuristic method called subproblem chaining. So it would begin with the logical proposition that it wanted to prove, and then it would generate a set of so-called subproblems that, if they were true, would lead to that desired conclusion in a single inference step. And then it would generate a set of subproblems for those subproblems in hopes that eventually the axioms themselves would be developed as subproblems. And if that happened, you could run that series the other direction and have deductive proof from the axioms to the conclusion. And they acknowledged, of course, that this was an extremely preliminary attempt to automate human problem-solving behavior, but they did think that they had achieved that in some way. And they also acknowledged, of course, that there's no guarantee that you will get a proof by this method. And that was fine for them as well, because they proposed that human mathematicians also have no guarantee that the proof search path they're on will lead them to a conclusion. And so they were excited about this. Famously, this was the only implemented program that actually ran, presented at the 1956 Conference on Artificial Intelligence, around which that term itself was coined. And more so than it was taken up in our automated theorem-proving, the logic theory machine was taken up in the early artificial intelligence community. In particular, this heuristic approach was put to work in the automation of medical diagnosis and of synthetic chemistry and other fields that early AI practitioners were interested in. So this was the model, this heuristic problem-solving model of theorem-proving that Newell and Simon wanted to automate. But of course, models don't compute. This was a fairly high-level vision that still had to be translated into an actual running computer program. They needed a way of encoding and storing and manipulating logical propositions in the Johniac computer that was amenable to backwards subproblem chaining. And that was a different project almost altogether. And sort of tellingly, neither Newell or Simon had enough experience or interest in working with actual computing machines to do this implementation work themselves. And so they had to enlist the help of a third collaborator named John Clifford Shaw. So after a career in aviation and studying engineering during the Second World War, Shaw took a position in the numerical analysis department at RAND, and it would later be renamed, of course, the programming department. And this department was sort of a service department that were the ones who got their hands dirty with computing machinery. Shaw actually reports that they called it the sweatshop. Of course, at that time, computers were extremely large and noisy and produced a lot of heat, and they worked in the basements, often without their shirts on, doing the physical labor of carrying boxes of punch cards from one machine to the next. This was where the physical work of computing at that time took place. And they had a more intimate knowledge of the limitations and capacities of the machines at that time. And Simon had much less to do with the implementation of the logic theory machine than he did with the design of the model. So Newell and Shaw worked together. And for many months, they were stuck on the problem of how to represent logical expressions, how to store them in computer memory in a way that was efficient and that would make it possible to do this sort of backwards subproblem chaining approach to theorem proving. And after a lot of experimentation of different possible structures by hand on paper, they settled on what was called the linked list information structure, or we would now call data structure. So data structures or information structures, as all of you know, are what they sound like. They're ways of structuring data in computer memory so as to be controllable and useful and meaningful encodings of all of the various things we want to put into the computer, as it were. And there are many different kinds of data structures, but linked lists were among the earliest and have also become some of the most basic and prolifically implementable data structures in use. I was very surprised to discover that linked lists were first created for the purpose of theorem proving, because you meet them, in your very first programming class, and that seems like kind of astonishing fact to me that they had a history or an origin at all, because they're so intuitive to us now. But in a linked list encoding, each element of a logical expression was represented by an alphabet of 6 values that indicated what kind of element it was, if it was negated, what position it held in the expression, and so on. And these values were stored in some contiguous set of bits in Johnniac's memory. And the last of those bits, that's here labeled Q, stored the numerical address of the next element in the expression, which could be stored anywhere else in the Johnniac's memory. So here, and very much unlike, of course, on the pages of Principia, logical expressions were not stored as a single spatial unit. They were distributed all throughout Johnniac's memory, held together only by this virtual string of address pointers. And they chose this structure not for a logical reason, but rather to solve a really simple housekeeping problem with the Johnniac computer. So for example, if you want to delete an element in service of this backward subproblem chaining, all the Johnniac had to do was reroute the address pointer from the previous element to the next element, which was one operation, as opposed to having to rewrite the entire expression with one fewer terms, or worse, create enough memory to do so, which would have made the task far less efficient, if not impossible. So imagine it's like if you have a list of guests that you want to come, that you've invited to a party and you want to keep track of who can come. It's a lot easier just to cross a name off of the list than it would be to rewrite the entire list with one fewer element every time someone RSVP'd in the negative, or worse, to try to find paper to do that. And it's such an intuitive and trivial thing, and yet this was the kind of innovation that made it possible to implement computer software in the 1950s, given the constraints of the machines, and you can see them rethinking what logical expressions are through the lens of the limitations of computer memory. And similarly, the inference principles from Principia were reimagined as 44 variations of 8 list processing operations. So while at a formal level they perform the same inferences, on the ground in the Johnniac, logical inference is being reimagined as find, compare, erase, replace different variations of list processing. And of course, they cultivated an entire programming language called the information processing language for doing these kinds of linked list manipulation operations, and reimagined logical proof and later all kinds of other human problem-solving practices through the lens of that language. It was designed entirely with the Johnniac in mind rather than a human mathematical agent. So of course, linked list logical expressions and the ones you find on the page in Principia are formally equivalent. The same things are true of them, but they have a slightly different character. Here, logical expressions are dynamic, they are processual, they are algorithmic. They have to be traversed one address pointer at a time. And Newell and Simon claimed, of course, that humans and machines were both symbolic information processors, but on the ground, the symbols and the processing were in fact quite different. And this is the sort of reimagining of what logical expressions are and what inference and deduction are, and the kinds of transformative rethinking that really interests me about this early work. So just some aerial thoughts about the logic theory machine. Even though what they wanted to do was preserve human practice, to highlight a deep similarity between human minds and machines through the lens of systems engineering at RAND, they could not help but transform the tools with which the work of proof was done, and they introduced linked lists and list processing to the arsenal of tools for doing theorem-proving work. Human reasoning they reimagined as information processing in this very particular way. They modeled human problem solving as formal, rule-bound heuristic application after Polya, and then in translating that model so as to accommodate the affordances of the Johnniac, they came up with this whole new toolkit of linked list data structures and list processing languages, and these were new tools for doing the work of logical proof. And they were very excited about the logic theory machine. I think it proved 38 of the theorems in the first 9 chapters of Principia. Famously came up with one new proof that was apparently unknown before. In a really lovely historical twist of fate, Bertrand Russell was still alive at this time and corresponded with Simon, and in that correspondence indicates both that the new proof that the logic theory machine found was more elegant than the one they had for that particular theorem, and also lamented the fact that if they'd known that computers would be doing this kind of logical proof, that he and Whitehead would not have spent upwards of a decade of their life doing all of those proofs by hand. And this heuristic approach was taken up throughout early artificial intelligence research. But there were a lot of critics of the logic theory machine, both of its efficiency, of the kinds of problems it would be capable and incapable of solving, and of this claim they made that there was some deep similarity between human minds and machines that they were exploiting in its construction. So one of the most vocal critics, or early critics of the logic theory machine, was this man, Hao Wang. And he thought that fundamentally Newell and Simon had made an error by mistaking a myth that fundamentally human mathematical faculties were rule-bound and therefore automatable in some simple way. That was just a mythology. He wrote later in his life, logicians had worked with the fiction of man as a persistent and unimaginative beast who can only follow rules, and then the fiction found its incarnation in the machine. So Wang, like many others who worked in early automated theorem-proving, thought that artificial intelligence had simply gotten it wrong. They had mistaken the character of human reasoning. They had imagined it to be too machine-like. So unlike Newell and Simon, Wang thought that the material substrata in which reasoning acts were carried out mattered a great deal. It wasn't just about some high-level formal processing. He wrote, a particular act of recognition or reasoning depends on one's genes, the history of one's mind and body, some essential relation to desire, even race, class, sex, and many other factors. Machines would never reason like people because they lacked experiences and training and specificity that inform people's ways of thinking. But Wang still believed that computers would be incredibly useful for mathematics, but it would be precisely because they were different from us and not because they were somehow alike. Computers would be interesting mathematical agents precisely because they embodied this mythology we had imagined of ourselves, namely that they could just follow rules blindly and unerringly and efficiently. So Wang, in the late 1950s, in large part in direct critique of the logic theory machine, developed a set of programs, one of which was called Q, that he described as being more like a slave than a human mathematician who could carry out these plotting exercises and perhaps open up some new pathways for mathematical problem solving that way. So Wang immigrated from China to the United States in 1946 to get his PhD in philosophy with Klein at Harvard. And his training and his career were all deeply rooted in the analytic tradition of philosophy and in mathematical logic in particular. But he also, in various moments throughout his published body of work, articulates a kind of dissatisfaction with analytic philosophy. And in particular, he was dissatisfied by the fact that analytic philosophy, at least in the tradition he imagined it, didn't appear to be particularly useful or applicable to the lived experience of daily life. And he thought that philosophy ought to be a guide to action, that its insights should be useful, that it should accommodate our thinking about everyday life and not merely be relegated to the realms of abstruse reasoning. And this attitude or posture or perspective may have come in part from the fact that Wang, and was quite open about this in certain parts of his life, was deeply influenced by materialism in China when he studied there growing up, and also through Marxist thought that he had varying relationships with throughout his life. He wasn't open about it until the 1970s, of course, but I think his partiality to certain elements of Marxism explained his interest in computing, his interest in automated theorem-proving, and informed this perspective he had about the need for philosophy to be useful. So he wrote much later in his life, near the end of his life in 1993, that, quote, although there was much that puzzled me in Marxism, I felt that I saw a comprehensive philosophy unifying thought and action in a way that I had not before considered possible. And this idea that philosophy should be useful or action-oriented was something that he recognized and appreciated in Marxism, but also I think something that he recognized and appreciated in computing. I think he saw in the computer the opportunity to take some of the insights of analytic philosophy and of mathematical logic and to make them useful in a new or a different way. Martin Davis, incidentally, has also conjectured that Wang was interested in computing because it might give him a more useful skill set to take back to China if, in fact, he decided to return there during his life. But he also saw in it a way of bridging thought and action, or logic and utility that was novel. So he wrote in 1960 that, quote, a common complaint among mathematicians is that logicians, when engaged in formalization, are largely concerned with hair splitting. It is sufficient to know that proofs can be formalized. Why should one take all the trouble to show exactly how such formalizations are to be done, or even to carry out actual formalizations? And Wang was troubled by this, that not even mathematicians in the 1960s seemed particularly interested in working with mathematical logical tools. But he thought that perhaps with the computer, logic could be made useful to mathematicians in a new and a different way. And incidentally, as an aside, I think that Wang's longer career was informed in various ways, and his larger body of philosophical work was informed by his relationship both to China and to Maoism and to Marxism. His archive is full of folders where he collected newspaper clippings about policymaking in Mao's China. He also penned a number of letters to the editor, some of which were published, defending certain Maoist policies and the collective vision of political life that was embodied in China. And although he divorced himself from Mao in particular, and also from Marx in the 1980s, after the reality of Chinese life in the post-war period became more visible to the West, there were still elements of Marxism that remained central to his project throughout his life, and in particular that it was useful in this way. That philosophy was supposed to be useful, and I think this motivated his interest in computing for sure. So after he finished his PhD, that's when he started spending time in different kinds of institutions than his home institutions. So he was lecturing at Harvard, he was also lecturing at Oxford in the philosophy department, but in the 50s he started spending summers at very different places, at IBM Research Labs, at Bell Labs, at the Burroughs Corporation, where he was interested in gaining a new skill set to work with computers, but also where he became interested in automated theorem proving that drew from mathematical logic rather than drawing from a vision of human mathematical problem solving like Polya. I also wanted to mention that around this time, the Marxism that may have inspired him also created some troubles for him. So in 1956, when he was traveling between Harvard and Oxford by boat, he was found transporting undeclared electronics components and also Marxist literature with him across the ocean. And this was reported to the FBI, who did a full survey of the electronics components he had in his possession to see if any of them were for the building of nuclear weapons. They were not. And he was under some surveillance following this moment for the rest of the 1960s. They didn't care too much about him, but every time he came and entered the United States, there would be some paperwork filed with the FBI, which I recovered through a Freedom of Information Act request. And there's a lot of troubling things to unpack about this, and I think it informed Wang's career in certain ways that are significant, but that's not the central focus of this. So for him, I think computing, this image though, this image of Wang sailing between Harvard philosophy and Oxford philosophy with a suitcase full of electronics components and Marxist pamphlets captures him, for me, in this very particular way, the sort of hybrid political intellectual character that his amazing career had. So for him, part of what computers offered was this possibility for tacking between the abstractness of analytic philosophy and action, a kind of utility. And just to give a small example of that, this program Q was designed to prove the exact same theorems as the logic theory machine, those presented in Principia Mathematica, but it would prove them in a completely different way, one that had nothing to do with human problem solving or with models of human pedagogy. It was not based on anything like that, but rather drew instead from mathematical logic itself. So one piece of the program was built based on Erbrand's theorem. So Erbrand's theorem offers a mechanism in principle for proving theorems from the predicate calculus in terms of the simpler branch, the propositional calculus. So it states that for some statement P from the predicate calculus, Erbrand's theorem gives a method for producing a corresponding infinite series of statements in the propositional calculus that simpler decidable branch. And then the theorem states that P is a theorem if and only if, for some n, the first n of those s's forms a disjunctive tautology, meaning that it's true no matter what values are substituted for s1, s2, and so on. So of course, one way one could in principle search for a proof would be to test whether S is a tautology for n equals 1, 2, and so on. And if P is a theorem, eventually a tautology would be discovered, and with it a proof. But of course, Erbrand's theorem was never meant to be an actual method for proving theorems. Even in really simple cases, you might have to check trillions of cases before you would find a tautology. I think in some cases you can calculate an upper bound on n, but it's too many cases for a person to check. And worse, of course, if P is not a theorem, you would go on forever never knowing if the next case would be a tautology, and it never would be. Erbrand's theorem represents a particular kind of result, very common and familiar in proof theory and in mathematical logic. It is a statement about the relationship between two branches of logic that is surprising and important. And even though it gives an in-principle method for proving theorems, no person could ever actually apply it, and that was never the point. But Wang thought that maybe there was something in Erbrand's theorem that the computer could exploit in a way that we couldn't, could put these logical results to work in a different way. So Erbrand's theorem was one of the logical components that he wanted to harness in his theorem-proving program. So he designed a method that he called pattern recognition. And he exploited structural properties in Erbrand's theorem to program computers to look for proofs of predicate statements. And the key insight here is that there are only ever a finite number of ways for that series of S's to fail to form a disjunctive tautology. Because each assignment that makes some S false might simultaneously force another S to be true, which would give you the tautology that you needed, and the computer could check those falsifying assignments. There would be a lot of them, so this was not a method that would be feasible for a person, but the computer, because of its efficiency at executing or discharging this kind of exercise, was able to put this insight from Erbrand's theorem to work. So Wang calls this the method of pattern recognition, but of course these are not patterns that we can see. These are computer-oriented patterns. His archival notebooks are full of these beautiful empty tables where he gestures to the method, but of course cannot himself execute it. So this was a very powerful method. It proved almost all of the theorems, I think, from the first 9 chapters of Principia, way more than the logic theorists and in far less time. But Newell and Simon were somewhat uninterested in this program because they said these are not the kind of proofs we're interested in producing. We wanted proofs that look like human proofs, proofs that we can read, proofs that are like the ones that we make. And Wang was not interested in harnessing the computer in that way, and rather called his slave. So he wrote, "The human inability to command precisely any great mass of details sets an intrinsic limitation on the kind of thing that is done in mathematics and the manner in which it is done. The superiority of machines in this respect indicates that machines, while following the broad outlines as drawn up by man, might yield surprising new results by making many new terms which man is not accustomed to taking. We are in fact faced with a challenge to devise methods of buying originality with plodding, now that we are in possession of slaves which are such persistent plodders." So this was such a different vision of the kind of contribution that computers would be able to make, and of the relationship between computers and people, and of the kind of proofs that we might want to get out of automation was very different from that of Newell and Simon. So just some summarial thoughts about the program Q. It was built to capitalize on this fundamental difference between people and machines rather than a perceived similarity. Also, he saw in computers this way of taking philosophy, of taking mathematical logic and making it work for us in a different way, putting it to work, logic in action, which fits into his sort of broader project of trying to find utility in the analytic philosophy that he spent his life pursuing. There's also, I think, here a kind of transformation in the character of Erbrand's theorem. It goes from being a statement about the relationship between two branches of logic to a toolkit for doing different kinds of automated work, and that seems to have been what excited Wang the most. And what comes out of this, of course, are computer-oriented patterns, algorithmic patterns, patterns that aren't for us to see on the page, but are rather to be discharged algorithmically by the machine. So I'll finish by saying a very little bit about this third program, the AURA, or the Automated Reasoning Assistant. And it was premised on the idea that perhaps the right way to use computers was not as standalone theorem provers at all, rather as assistants or interactive partners for a human user, but that still might open up some quite new ways for doing theorems. And in that sense, it's kind of a critique of both of the others. And AURA was developed at the Argonne National Laboratory, which was also founded during the Second World War in association with Fermilab. And automated reasoning or automated theorem proving work at Argonne took place in what was called the Applied Mathematics Division. And that division was a lot like the numerical analysis department at RAND in that its primary purpose was to be a service department to the other groups at Argonne who needed their software implemented, needed calculations and simulations run. But due to Miller, the director of the Applied Mathematics Department, it also became a really exciting site for automated theorem proving research for its own sake. And it became more and more like that as the study of computers and computing for their own sake became more prestigious and more pressing in the American academic landscape. And so one of the things that William Miller, the director of that division, did very early on was to hire this man, Larry Ross, who I imagine many of you know. And Ross, of course, did not believe that we would be able to program computers to do the kinds of things that people can do. And this would limit their possibilities for contributing to mathematics. At one point, he wrote that proving theorems in mathematics and logic is too complex a task for total automation, where it requires insight and deep thought and much knowledge and experience. And somewhat in the tradition of folk psychologists or philosophical psychologists like Jacques Adamar, Ross singled out intuition in particular as something that would be patently unautomatable. I've interviewed Ross, and he has described to me eureka moments that come in the shower or while you're washing dishes or while you're walking or even while you're sleeping, and that clearly whatever process leads to that kind of insight, intuition about a problem is not rule-bound, at least in any way that we could formulate it this time, but that you might need insights of that kind in order to do interesting and exciting mathematics. So that's why he imagined instead a kind of collaborative, interactive theorem-proving architecture in which human users could impart their unautomatable intuitions and insights about a problem, and then the computer, because it is such a powerful, rule-bound, plodding slave in Wong's terms, could then follow those intuitions to conclusions faster, further, and perhaps in different directions than their human counterparts might be able to. So the Argonne group was tasked with architecting an interface. There would have to be the human contribution, the intuition, the guiding insights, and then there would be the computer contribution, the mechanisms by which the computer would follow those intuitions in hopes of solving problems and discovering theorems. And the creation of AURA, in building this interface, really interesting and I think surprising and important things happened on both sides. So even though the Argonne team cordoned off human intuition as something uniquely human, something unautomatable, they still had to rethink what intuition was in order to make it usable to the computer. They still had to reimagine it through computational terms so that it could be made into input. And that part of the program was developed in 1971 by a man called Ross Overbeek. It was his PhD dissertation at the University of Illinois, and he reimagined human insights or intuitions about a problem as a weighting mechanism. So in the reference manual for AURA, it's described as, quote, weighting is the process that assigns measures of complexity to clauses in the clause space. The definitions of complexity can be chosen by the user to reflect some predisposition that may be, for example, based on an intuitive notion of how to direct the proof search. So weighting allowed the human user to provide their preliminary sense of what kind of information would matter for a given proof or a given problem. They could assign a quantitative value to propositions of a certain form, to inference chains of a certain order, or to other kinds of information using these weighting templates that they could input at different stages in the search for a proof. So users could say that addition is more important than multiplication, or that the sum of two sums is more important than the sum of two products. And these values would lead Aura to preferentially pursue those inferences whose ancestral clauses had the highest concentration of relevant information as intuited by the user. And users could also restrict Aura's search, prevent certain search paths by inputting clauses that the program was forbidden to produce. And so this weighting mechanism was one of the ways that human users were meant to transform their ideas or insights about a problem into input that the computer could use. But when I discovered this, I thought this was so amazing because here they cordon off intuition as something uniquely human, describing these eureka moments that have a kind of esoteric magic to them. And then they get translated into the weighting mechanism, which is something quite different. And it represents that even when we cordon off uniquely human faculties, if we want to make them useful or usable to the computer, they still have to be reimagined through the technical vocabulary of what computers could use or put to work in an automated system. And this was the kind of thing that got me really excited about this project right in the beginning, where these kinds of reimagining even of human faculties that are held apart. So that was the human side, or one part of the human side of this Aura collaboration. Intuitions or ideas about the problem were given to the Aura as a weighting mechanism through these weighting templates. And the other half, the computer contribution, or one of the computer contributions to this collaboration, was developed by John Allen Robinson in 1965. So Robinson was a classicist who had studied the long history and part of logic, but starting in 1961, he began spending his summers at the Argonne lab as a research associate, and there developed a relationship with this theme in the applied mathematics division and an interest in theorem proving. And Robinson, like many others working in the field, also believed that computers and human minds were just qualitatively different entities, and that there was no reason to expect that the logic they used, the methods they deployed for theorem proving, should be the same kinds of reasoning or practices that people use. But Robinson then went further to propose that maybe we should be rethinking logic in general in a way that was oriented more towards what computers could do than what people could do. So in 1965, he published a paper in which he introduced the famous resolution principle, but he framed it this way. He wrote, quote, "Traditionally, a single step in deduction has been required for pragmatic and psychological reasons to be simply enough, broadly speaking, to be apprehended as correct by a human being in a single intellectual act. When the agent carrying out the application of an inference principle is a modern machine, the traditional limitation on the complexity of inference principles is no longer very appropriate. More powerful principles, involving perhaps a much greater amount of combinatorial information processing for a single application, become a possibility." So he didn't just want to posit that people and machines were different. He wanted to construct new logics, machine-oriented logics, that were not constrained by the limitations on human psychology, that were not designed, like Russell and Whitehead wanted, to capture the irreducible steps of human reasoning, but rather he wanted inference principles that were sound, but need not be oriented towards human psychology. And this was a sort of a larger step. And he introduced one such rule in 65, the resolution principle. One way to describe it is from two parent clauses that are disjunctive series that contain complementary literals. So one contains a literal that's the negation of the other. With resolution, you can resolve those two parent clauses into a child clause with no instance of that literal P. But more importantly, it has a slightly different character, this rule, from some of the more traditional ways. This is, of course, just a baby rule, but the syllogism, Socrates is a man, all men are mortal, Socrates is mortal. We are supposed to be able to draw that conclusion and not require any further explanation. This is supposed to be a self-evident principle. Whether it is or it isn't is, of course, another question. But in Robinson's language, this was meant to be perceptible as correct to us in a single intellectual act. Here is a baby prose example of what resolution permits us to do. From the premises, all hounds howl at night. Anyone who has cats will not have any mice. Light sleepers do not have anything which howls at night. John has either a cat or a hound. We can conclude that if John is a light sleeper, then John does not have any mice. So this is a simple problem. It's not actually very difficult to work out. but it demonstrates that this kind of rule it's different in kind from something like the syllogism. It's not built to accommodate what is immediately perceptible or self-evident to us, only to be sound. And this turned out to be a powerful rule. I think it's the only rule that you need to prove most of the theorems in Principia. It's a very efficient rule, but it's not designed to accommodate human access or human understanding. And with resolution, Wallace got exactly what he wanted, a powerful rule of inference that would capitalize on what computers could do better and differently than people to follow human intuitions through these large inferential spaces in different ways than a human might be interested or able to do. But with it came a sort of displacement of human access. Resolution proofs were not so easy to follow, to read, to parse, to understand step by step. And that is part of the conversation that surrounded resolution later. So this was the human-machine collaboration, or parts of it as architected at Argonne. Intuitions as weighting mechanisms were input to the machine, and the machine would then deploy powerful rules of inference like resolution to follow those intuitions further and in different directions than the human user might be able to. And of course, Aura surprised its users. It turns out that it accessed corners that human users weren't anticipating, and there were moments when it surprised its makers, which is always really fascinating, of course. And they described it as a colleague that made possible for them new and different kinds of problem solving than otherwise would have been possible. They wrote, researchers involved in the effort knew and know almost nothing of the fields from which the questions were selected. Rather than indicating the triviality of the questions, some of which are far from easy to answer, this fact shows the potential value of having access to an automated assistant, a colleague in the form of a theorem-proving program. So in designing and implementing the Aura, this team partitioned the work of proof into two quite distinct parts: the intuition that was cordoned off as uniquely human and patently unautomatable, and then there was the work of inference, which would be handed off to the computer that was better suited for powerful and efficient inference. But then both sides of that equation were reimagined through the lens of the computer. Intuition was redesigned as a kind of weighting template to guide the search. And inference itself was reimagined through this project of developing computer-oriented logics and became the resolution principle. And of course, resolution, its significance for the history of automated theorem proving can't be overstated. It was such a powerful rule, and so much work was done then, and I think still, to design variations of it, generalize it. And lots of the systems that were built later had resolution and variations thereof built into it. But there were some who worried that in that moment also something had gotten lost. Human access to the knowledge that we were producing might have been displaced through the design and implementation of logics and modes of inference that did not have our psychology or understanding built into them. Proofs were difficult to read. Some people thought that maybe they would offer us a certificate that something was the case, but maybe that they couldn't show us why it was the case. So one such person, of course, was Woody Bledsoe. He worked for a long time on generalizing and understanding and automating resolution through the 70s, but eventually he decided that it wasn't the way he wanted to do the automation of proof. The earliest written account of that I found was this one in his archives from February 1975, where he wrote, "I have abandoned resolution for the reasons that A, it appears to be ineffective on hard problems, and B, it is difficult to understand what is going on in the process. So, 1, humans cannot easily use the knowledge of the ages to make changes in it so it can be more effective, and 2, it is not easy to use in an interactive system."
Stephanie,
Another person who articulated some anxiety about resolution was John Allen Robinson, who in 2012, speaking at a conference on automated deduction, where I had the opportunity to meet some of you, said that, quote, "In fact, formalization is not the thing we do when we're interested in the truth." He said also, "It's no good just following step-by-step a proof and saying, okay, if you don't really have understanding, if you don't really know what's going on, you haven't really understood a proof if all you did is verify it. It's only if you look into the ideas under that sequence of inference that you have understood the proof." So by the 90s, and even maybe today, there's still this tension about whether formalization or human understanding ought to be privileged in these automated efforts. But more than that, there's a sense that what it even means to formalize and what it even means to intuit are partly on the table as moving targets in this history. New formal tools and new ideas about what intuition is are changing all the time through the story. And that's something that I'm trying to recover from the very early moments of this history. So here's sort of a summary of those things, and I'll stop there because that's a long time. So thank you so much. It was really a pleasure to have a chance to share this little bit of this work with you, and I'm sorry I can't be there in person.
So, can you hear me, Stephanie? That was absolutely fantastic. So, Stephanie, that was absolutely fantastic. I'm not sure if you could sort of see us flapping around thinking, on the one hand, we want you to go on for another half hour. On the other hand, we're trying to get the next thing going. But I have lots and lots of questions after that, and I think everybody else has too. You couldn't see that little thing in the corner, I think, when you were speaking, but you had us with rapt attention, all sorts of people listening, nodding, you know. It was fantastic.
Nice, that's cute. That's scary.
Sorry, what are you trying to do now?
Can you finish the introductions to the staff?
Okay, if you can stay there for a moment, we have a little bit of business to do, and then we will just come back to you.
Sure.
Let's see. So, you know, it's the moment in the workshop where we have to thank some of the people who've made everything possible. So, you know, I'd like to thank the staff at Newton Institute profusely for you know the great work they've done. Actually, I know most of you by your first names, but you know, I'll try and introduce you. And Christine help me if there's any issue. So this is Christine Marsh, she's the deputy director. There's David Abrahams, who's the director, and then there's Dan, Vincenzo, Paul, I don't know, Jill, Catherine, and Megan, and Che, and Anel.
First week.
Yeah, great. So please give them a big round of applause.
I just want to say that, you know, anybody who's ever done anything administrative like this, you know, we all fantasize about you know, having the perfect administrative staff that would, you know, just get rid of all that. But you guys were even better than any of us could have dreamed. I mean, you were just amazing. So from the bottom of our, we're all having a great time, and we thank you from the bottom of our hearts.
Thank you very much. Which reminds me that, you know, for this workshop, we actually you know, have to thank Jeremy and Ursula and Andy Pitts and Larry Paulson. So again, please give them a big round of applause. Now back to you, Stephanie.
So, Stephanie, so I think Shankar, you wanted to get your panelists geared up and so on, and we can multitask getting the next session started and seeing if there are any questions for Stephanie. Are there any quick questions for Stephanie? Every slide could trigger a whole essay, which is great. But Jeremy.
Yeah. So Stephanie, it's a shame that you're not here because we're still debating exactly the same questions, which maybe indicates that we haven't made any progress, except that computers have gotten better. But what I wanted to ask is, it's striking that all your case studies were American, started in the United States. So can you tell me about why you think that is, and were there things going on elsewhere, and how did the ideas transfer?
It's a huge oversight, and the answer is basically a practical answer only, which is that as a graduate student, I didn't have the resources to travel to Europe, visit archives, and do practitioners there. And one of the steps out for expanding the project to attend to some of what was happening in Europe at the time. On the other hand, there is something to the national context of the American Cold War, which I think informs so much of the work that was done in the United States as a way of bounding the kinds of projects that I study. And that's a very artificial kind of boundary. Historians have a bizarre and I think really problematic way of nationalizing themselves. So I am technically an Americanist, which means My political history is around the American 20th century, and that's not how I would like it to be. It's just a sort of practical byproduct of my training that I think has excluded a great deal of work that was done in Edinburgh and in other parts of the UK especially. So that's just a problem.
I was actually a comment. One thing that always amuses me is that Bertrand Russell, of course, lived a very long time, and he actually had a correspondence with Herbert Simon, and it's always somehow a cultural disjunct in my head. It wasn't entirely clear that Bertrand Russell knew what was going on, but the idea that they were closer than one might think. Any more quick questions, or shall we? Stephanie's on email. We're going to get her over to Europe real soon. And any more quick questions? No. Well, great. Thank you again. That was just one.